We're live.
Hey everyone, welcome to another life science stream. We're continuing with our roundtable format. So I think we're going to go around the proverbial table and discuss some of the work that we've been doing over this past week. The contributions do tend to vary, since some research is more theoretical than others, or some research is at a more theoretical stage than other pieces of research. But we'd like to give everyone an opportunity to share with their colleagues as well as with our greater community the work that we're doing on a weekly basis. And so I think we've agreed that Richard will go first. So, Richard, often you have found yourself relegated to the tail of these streams. So please, I think
Hmm.
I speak on behalf of everyone when I say take your time. Um,
But I think once it happened, and I didn't even need more than that, the half hour anyway. So um, I
what
it's
kind of
all
cheese is that? What kind of cheese is
it's,
that,
it's
by the way?
it's mozzarella actually. Yeah.
Oh, okay. That's a soft cheese is probably good for a live stream because it can be chewed more
I'm
quickly, I
kind of
think.
cheating though. I'm kind of cheating because it has carbs, and I want to stick to just only meat at the moment, meat and eggs and things. So
I've
um,
heard that carbs that are off camera don't count.
uh,
That's something I learned in
so
LA.
I'll just do
Yeah.
this. Anyway, all right. So uh, we had some results before, and I in our Discord had posted them. And sorry, yeah, here. So we had some results
hmm
before. We were,
hmm
we're talking about this spatialization of computation and how this arithmetic Turing complete behavior gives us the ability to at least probe it in some kind of, loose sense of a space. And I noticed there were some difficulties with that, where you would have, especially if you were to enumerate it with this kind of, like I did here, which was some kind of, hypercube kind of thing. You're whatever, just some higher dimensional thing, and then you're building some. Essentially, I'm just flattening 6 dimensions and then building the program, three instruction program from that, and
Yeah,
then
actually,
yeah.
if you don't mind, this raises a question maybe for
Mhm.
Nick. I always feel like, and this is not an insult to you by any means.
No, no,
I
no. I
always feel
could do
like
this better for sure.
I always feel like a chump when I find myself using like 8 tables because I
Yeah, yeah,
certainly
yeah.
have done that
No, no, no.
before. And
I was wondering about this.
is there a better, yeah, Nick, or anyone else?
I'm sure there's a
Is there a
function that,
is
yeah,
there a way to avoid like because obviously you can have a table where it's for M and N and I, like you can do that, but it's not what you're looking for when you have to nest these tables. Is there a better way to avoid just having like a furniture store's worth of tables in your
yeah,
code,
there must be
like an
some. I mean, you just
IKEA's
have to
worth of tables? Yeah.
use some nice tricks.
Create all the tuples first and then map forward.
Mhm. Yeah, but yeah, I mean, I want to sort of, what am I doing? Yeah, 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 yeah. There's a smarter way of doing this. I was just very results focused at the time. I was like, screw it, let's just get this plot and ask questions later. So the problem with this is things like equivalences, as I mentioned before, where you have like, I don't know, 1/2, 2/4, etc. And
Hmm.
there are some others, but what that made me think of is things like Cantor's pairing function, where you you're sort of moving through this. This is this snaking path that you can take through Cantor's pairing function. So, for example, the 1/1, all these marked in red, 2/2, 3/3, 4/4, and so on. Those are kind of removed because you've decided that they're all equivalent. And similarly, the 1/2, 2/4, etc. I don't need to labor the point, but just for people following and things. Again, 1/3, 2/6, etc. So, and what you get, and so I sort of implemented that here. Actually, there's a better way of doing this. I looked at the wiki page for it, and there's actually some sort of closed form way that you can get a nice path through this. As you can see, Mathematica already does the simplification for you, so you can see that there's
Hmm.
ones down the diagonal, and you will find
Hmm.
halves in multiple places. Anyway,
Hmm.
I do this snaking path, remove the duplicates, and I get this set here, which now no longer has this problem of sort of duplicated fractions. And then again, I do that trick from before, but instead of having to have, six nested tables, I only have whatever. Um,
Four.
for some reason, I have four. Oh, because I decided to go up to four instructions, but actually, it would just be three. So it's
Three.
half the number. Yay! Look, progress. We've half the number of nested tables.
Yeah, and then we
Um,
added one. Yeah, yeah.
yeah, and I added one just because we don't want to be too good here. Um, so this has removed the problem that I was experiencing, but it sort of highlights another, which is that you know programs which say begin with an integer or which have duplicated instructions and so forth will cause these holes in the space. So in the other notebook here, um, I actually make a comment about this. So um, yeah, if you were hoping to have some kind of isotropic space, you're sort of out of luck, as there are sort of these holes that we need to remove programs with repeated entries. Yeah, so I mean, I was thinking about sort of anisotropic and isotropic spaces and uh, how you might sort of define these. And then a notion came to my mind because and this here that we should be familiar with the sieve of Eratosthenes, this process for which you can generate primes. Um, let's for fun just describe it. So we start at two, and then we just take all multiples and remove them, and three and so on.
Hmm.
And similar to the Cantus pairing function, there's sort of like this notion of equivalence classes or whatever, sort of like all multiples of two are some kind of equivalence class, two being and all the others are some sort of composite number, two being the prime, three being the prime, five being the prime, and so forth. And I started to think about this idea, like, what if you had the notion of a prime program? And that is like
Hmm.
a program
Yeah,
that is
yeah,
the sort of,
yeah.
yeah, like the equivalent of a prime number in the sense of a program. And I found an example,
Hmm.
and the example is as such. If I can if I can find the background thing. So this max function here, if we restart it, um, oh, it's yeah. So So this one, you have two inputs, 4 and 7, and it will eventually speed up. We'll stick the answer in the 5 register, and the answer is 7 because it's the maximum number. If I change the first argument to 8 and run it, we get 8. So it works. Um, so there's some kind of semantic notion of what it means to be a sort of maximum function, but we can sort of treat that as some sort of generator or some sort of prime, which um, you know, is the root of all those equivalences. If you say change the numerator and all of these fractions to the number 11 instead of 5, so we have this program. It's a different point in space, but now restart it and run. Our answer now is on that register. So do you get the point I'm trying to make here? So that, and then yeah, if I change that, just to show you that it works, if I change the first argument to 6 and run it, oh, what's happening? Oh, sorry. Yeah, the maximum 7 is correct. I confused myself for a second, but yeah. So we have the correct answer 7, and if we make the first argument 8, then the maximum is 8. So um,
Hmm.
yeah, and so I said the minimal program forms some sort of equivalence class n over 6, n over 2, n over 3, which would be the sort of generator or whatever. And you could also think of introducing redundant instructions ad nauseum whilst maintaining invariance of the semantic properties of the program. So within the moduli space question, the question posed to me when I joined the institute, this provides us with a kind of space of program semantics as opposed to just a space of isomorphic causal graphs, which I think is a little bit more meaningful on the computation side. Maybe not on the physics. On the physics side, maybe you'd be more interested in the causal graph isomorphism. But
Well, this is basically a computational project. So
mhm.
if we can find ways to
Yeah.
if we can find ways to spatially parameterize programs as opposed to
Mhm.
computational behavior, personally, I think that's even better. So as I've
Cool.
said to you many times privately,
Yeah.
if yeah, so
Yeah.
okay.
So
Hmm.
I don't know. I just started thinking of that because first it was like, well, I want to use this pairing function as a practical thing to sort of simplify the space and remove redundancy. And I was like, well, there's some similarities between this and sieve of Eratosthenes, and that's the notion of a prime program. And actually, if you Google prime program in Google, as I would, because I
Mm.
want to see if there's existing research, the top result is
Sure.
something to do with the matrix. So,
What the
Car
film?
yeah, the film. So I don't know. I'm just saying that as a little joke because I know Carlos mentioned
Carlos,
it.
Yeah.
Carlos's recollection of the details of the Matrix are pretty impressive.
So
Uh,
just Google
do you know what?
prime.
No, no, sorry, guys. For people who have just met Carlos, he has other talents as well. It's not just Carlos isn't at the institute just because he can recall things
How
from the
is that a
Matrix.
talent even?
It's not a talent. um,
It's a
okay,
lifestyle.
hold on. I'm curious, Carlos. Do you know what this prime? Do you know what that thing is
Well,
from
I don't know.
the
I
film?
was
Well,
going to ask,
I
like,
I
what is it?
well, if you just Google prime program, it's the first result that I got, and it's some kind of wiki fandom thing where they describe something in the movie. I don't know. I don't. You guys can do that. And
Ah, I think I
Was
I'll,
know.
it
I think I
was
know.
it the name of the nightclub in
uh,
Matrix Reloaded? Because that
it's
would be a
something to do
good
with
name
like
for a nightclub.
No, it's
it's like
the. Yeah, I know
it's
what
like
it is.
that's Neo's mission or so. I can't remember.
Yeah,
Yeah.
yeah.
Anyway,
I know what it is.
I should have just stuck it in this workbook. Um, I did have something else to say a little bit, but I think
It's just that
yeah.
also they use the word program a lot because it's almost synonymous with agent and
Uh,
like, and they use program because it just sounded, it's the 90s, so it sounded cool. Instead of people like the inhabitants of the Matrix are programs.
Hold on. And here we have yeah this. Well, I mean, I don't know if it sort of makes sense, but the prime program, at least in this sense, it's not nothing really to do with. I mean, as you extend the length of the program, then it does become some sort of Kolmogorov thing. But at least when they're the same length, it's just maybe perhaps that they're sort of numerically the minimal thing. But the idea of some sort of generator and then yeah, and now you can sort of quotient or collapse all of those other points down to this one single point. You've essentially sort of
Hmm.
encapsulated the behavior of a whole class of programs, even though they produce a different output. They're sort of doing the same thing. In this case, it's a very trivial example because all I'm doing is just sticking it in a different register. But you could come up, and I will try to come up with sort of more things. And one of the examples was this idea of redundant instructions. So things in there which are not really, they're maybe doing and then undoing their work and leaving the result unchanged, um, and so forth. I think I had some other points, but if anything comes to mind and you want to talk about it, I'll think in the background.
Well, what prospects are there for, say, visualization or kind of generation of these spaces besides just the array plot? The array plot is
Yeah.
a helpful way of
Well,
beginning, but what do you have any ideas?
I mean, maybe graphically, this as in connected graph, maybe there is some way in which, yeah, you could. I mean, is this some sort of like weighted adjacency matrix or something? No, I mean I've just flattened some sort of high dimensional thing. I mean I reduced the number of dimensions by this Cantor pairing thing down to three, but we want to look at longer programs. So yeah, I'm not too sure off the top of my head. And yeah, I mean it's not in the sense that these are sort of invalid. It's just that mm, that they don't make sense. It doesn't make sense to put an integer at the beginning of a Fractran program because that's essentially an infinite loop with a bunch of dead code after it.
Yeah, that's
Yeah. And oh, the other thing I wanted to talk about a little, just very briefly was that self-interpreter thing, which is to say that, from those we know the existence of some really long jumps, to because the self-interpreter is some 20 something instructions, and then there's some encoding procedure by which you need to take the initial state and sort of transform it so that it's digestible by the self-interpreter. But that suggests that there's, some very non-trivial ways of jumping to semantically equivalent programs. And how to sort of give a sort of rigorous mathematical treatment of that, I'm not absolutely sure right now, but it's kind of an existence proof already because I've already given an example of just like 2 + 2 within the self interpreter, which was from 3 steps to 3,000 steps. Semantically equivalent, takes longer to run, is a longer program, is a different point in program slash initial state space. But yeah, to come up with some sort of mathematical treatment to formally specify that under the language of moduli spaces and so forth, I'm not sure.
Well, this is slightly distinct from the moduli space question, but Łukasz, do you have any takes on this? Maybe for whatever reason, maybe you might have something to say about this whole thing.
I don't know, like I'm not really. I'm not really in the process of this research. I'm not following entirely what's going on here.
Yeah, I mean, I probably don't know where I've gone wrong to not explain things properly. Maybe yeah, I mean, the Fractran is kind of an alien looking thing, right?
Yeah. That I know. Yeah.
Okay. So I mean, yeah, essentially
You
it's
are
like
trying to parameterize the space of possible Fractran programs.
yes, and up to some sort of semantic equivalence in that the behavior of the program is the same, even if the output is different. It's from a semantic standpoint, which is slightly outside the system, we can still say that it's performing the max function. In this case,
Yeah.
in this case, it's a max function. And all I've done is just change the prime, which is on the numerator for each one of these to change its output register. But like I said, you could introduce some sort of redundant instruction. This doesn't work. But let's say I was trying to find some, but I wasn't successful. But I will be successful in finding some instructions which don't really change the final result. So the program stays semantically equivalent, has some redundancy. And you could think of this as some kind of compression down to some, as I said, in terms of the Kolmogorov complexity or something like that. To a lower Kolmogorov complexity whilst maintaining, semantic property.
So,
yeah.
Do you know what you're actually modding out by?
Well, yes, by some sort of formal specification of the semantics, yeah. And your choice of language for that is somewhat arbitrary. Like the program does X that I want it to do or something. Even if it's doesn't matter where it puts the result, doesn't matter if it spreads the result out. Maybe another example, but yeah. And it's not just again, it's not just programs that terminate. Like I often find it frustrating, sort of bouncing between the world of functional and imperative. It's like I remember when I first encountered programming, like the idea of the language used the keyword proc, and I always thought of them as procedure. And like procedure sort of makes one think of process. And yeah, functions are one thing, but procedures are slightly different. They may not terminate. They may do crazy things, all sorts of crazy things. They're not essentially mapping some input to an output. They might not even have inputs, So the notion of so I guess then you need to start. Yeah. Right now I'm just looking at the output of some function, but if we were looking at the behavior of some
procedures might not have inputs.
Well,
I don't know anything about this.
Well, they have some sort of initial state, but it's not really quite an input. For example, the prime generating function, Fractran program or whatever, it starts with the number 2, but it could start with any other prime. Is my point? It doesn't match. 2 isn't special. I could start it with 3 and
Oh,
it'll still do stuff. But I mean, you could also modify the program so that it's doing the correct thing. But in fact, wait, hold on. Let's just see what it does if we do that. 2 to the wait, faster. Oh, so it still generates the primes just fine. Okay.
by the
But if I'm
way,
yeah.
and I'm not an advocate of like reinventing the wheel in Mathematica for its own sake. Obviously, that
Uh,
would be kind of a waste of time if the institute just did that. But have you ever thought of making something that like would it be helpful if you had your
hmm.
own version of this instead of just using it on
Oh
GitHub?
no,
Um,
there is the resource function Fractran, which is what I've used. I mean, and that's how I
yeah.
generated those plots and so forth.
No, I
But
know.
oh, to make an animated thing or
I don't know.
yeah. I mean, what I'm interested in sort of exploring more is that quite often when people are writing these things, they actually deal with the prime factorizations. They don't put them into sort of, these integer quantities here. And then, if we remember, there's Conway's, where is it? Uh, you know, this representation of the programs, I want to sort of dive into a bit more because it might help in the process of constructing and working with them, building my own. That
Oh
he seems
yeah,
to, yeah. So he has
yeah.
these sort of
That
like
would be a good idea.
states and
Yeah.
yeah, transitions and so forth, and then you can sort of flatten it. This is actually hold on. In fact,
Yeah,
because we've got
like if you look at the fraction like that, you can actually work with the general theory of finite automata,
mhm. Yeah,
right?
I mean that's the connection with the Minsky machines. They're just finite automata, but along each edge they can manipulate some register. In Fractran, we just have one register. But in Minsky machines, you can sort of work with any sort of arbitrary number of registers or stacks. You can push things onto them, pop them off. Essentially, Fractran is like the most trivial Minsky machine with a single stack and a single symbol, and you're just pushing. Um, that's how you sort of that's how you have your state. The natural number state is just the number of how deep the Minsky machine stack is. I can't remember where, but oh, sorry, actually, it's this. No, I had it somewhere. Oh yeah, here. Um, he also describes a variant with a true with oh yeah, so Minsky describes a variation which is true and complete with only one register. It has operations to multiply the register by a constant and check to see if it's divisible by a constant, which is what you need for Fractran basically. So this is yeah, it's essentially the same, and I think that's where Conway got his idea. He's just he's just reframed it within arithmetic, basic arithmetic. Yeah, these are nice, and they sort of make me think of like these control flow diagrams. These are the Minsky machine diagrams actually. So you have your states, and then along each edge um, some operation that you perform, and then you bounce around your states. But actually, whilst we're here, why don't we compare this with the Fractran program? So we've got
Hmm.
maybe a bit difficult. I have to sort of pop this out and move it here and do this and um, oops. What was I on? I was on the Discord. Oh,
Now that you use our internal Discord as a way to
mhm.
find files, I have to really be careful what I say. Uh,
Well, I mean, my heart is racing because I'm uh, live and going through all my tabs and things. I don't, who knows? So, um, right. Yeah, I don't see any correspondence between these, but there are sort of multiple versions of this program that I've seen kicking around. So we might not like if you can find a 51 or a 1/5. I think these are again I think we're dealing with semantically equivalent but different programs. Uh, it's unfortunate because it would be nice if this particular it Conway calls it prime game, and I'm not sure if this um, online demo thing is actually using the same one. To me, it doesn't look like it. I can't see any similarities here. Over 549. No. Anyway, um, if you were to input the prime game, I actually have it in a notebook somewhere, but Yeah, so working at this level might help in order to think about transformations to this graph that leave the semantics unchanged, and that becomes some other generator of this set of
How
equivalences.
how self-interpreters look at the level
Oh,
of this
oh,
finite
that's an
dimensional
interesting
matter?
question.
Like
Hmm,
comparing the geometries, maybe.
that's an interesting idea. Yeah. I wonder how to do that, how to go from the program to this graph representation. My understanding is that the edges here are the actual instructions, but I'm not sure what the vertices are trying to say. I didn't sort of fully get it.
Like the vertex is the state that you
Yeah,
will write, and yeah.
but it's not the state as in the state of the running program. Yeah, it's just some sort of label for the state, but I'm not too sure. So yeah, I need to understand that a bit better. But yeah, it would be interesting to look at the self-interpreter. It's not that many more instructions than this, but uh, they involve far more primes, so the numbers are much, much bigger. And yeah. But looking at the graphical representation of it, I think would be quite interesting.
Yeah, I don't know if we could read anything from graphical interpretation of from this picture of self-interpreter.
Hmm.
It's, but yeah, but developing some formal methods to actually comparing them, maybe. Yeah, can we define a notion of isomorphism of this structure that
Hmm.
is really an isomorphism of the programs of what they do?
Yeah, yeah, yeah. Yeah, is there some constructive way that you can get from the base universe program to the self-interpreted program? And yeah, again, like, is there some way of relating this to other notions like, I don't know, projections and so forth, or maybe in a loose sense, but trying to draw parallels between the language that's used in sort of
Like,
existing
yeah,
mathematics.
if we had like this program for pi and
Hmm.
self-interpreted program for pi, can you just project from the one into the other?
Yeah. And then as it's running, the states, you will be able to find correspondences between them that, once we reach this point in self-interpreted, we can say that this is a direct correspondence to the state in the
Mhm.
simpler version. But the intermediates have no sort of, I mean, that was the reason why I looked into this, because when you guys introduced me to this idea of computational fine graining, I was like, okay, this is a nice way of thinking about how to sort of get the universe to slow down in a sense, or to
Mm.
insert more sort of stuff in between each state. Um, and this is one way of doing it. The compiling between things was another way which you guys were exploring. And but yeah, you can sort of nest these ad absurdum or whatever. So yeah. But I mean, you only need to
Yeah,
do it
until you go
once
continuous.
until you go continuous. And yeah, and I'm sure you have some nice points to make about the mhm, this the
So did we just lose James?
oh, I think
Yeah,
we did.
Okay,
his
Oh,
computer
he
died and we coming back.
he
interesting.
didn't plug it in. He missed the best bits because I think that's my part over. Have I taken up 40 minutes? I'm sorry.
No, no, no. Well deserved.
No, I mean it's really kind of it's more notional than
James is back.
anything concrete. James, we see you, but we don't see you, nor hear you.
Man,
Hey,
does anybody do continuous automatic?
well, I mean, you can think of like our analog recurrent neural networks as some kind of continuous automata. I think, like in the true sense, analog recurrent neural networks, which are just a sort of model. But that's the Ava T. Siegelman, her
Continuous
work.
automata.
Yeah, Yeah, if you look at Hava T. Siegelman, the analog recurrent neural network, she actually uses that as a way of uh, describing super Turing computation, and they sort of they relate it to things like Baker's map and some of these other
Who?
things.
Who?
Hava Havat and then Siegelman Siegleman I think Hava T. Siegelman and the analog recurrent neural network. Um, so it's like yeah, continuous computation, analog computation, not discrete dynamical systems. It's the same setup as a recurrent neural network, but um, with continuous time, continuous states, true continuous states, and so forth. And also, yeah, when you allow it to be self-modifying, when you allow it to adjust its own weights, then they make the argument that it's capable of super Turing computation when it can. But I mean, I just skimmed through a lot of that stuff. It's I don't know. I find sometimes that even Stephen wants to say once you're at the level of Turing completeness or whatever, you're universal. But those works suggest that no, that there is some sort of yeah
Yeah, like there's an infinite hierarchy.
yeah. But cool. Please, somebody else, somebody next, or if
Pukash? Nick?
Yeah, like maybe I'll just. We wanted to show something during this stream, but we're not ready yet, unfortunately. But we're getting closer with our understanding. Like I think we actually understood the Harshchandra isomorphism, for example, at the level, at least at the technical level, right? So we were able to compute it, and yeah, in a week I'm gonna have some nice examples to show. So
I won't bludgeon anyone with Langland's lingo, but basically, one of the unique things that Langlands did was introduce this thing called an L group. Representations of this L group are one of the two representations that are used in automorphic L functions, which is kind of the L function by which we extend ourselves into non-abelian class field theory, which is one of the goals of Langlands. But this L group is constructed through this thing called a Langland isomorphism. And this thing depends on a previous isomorphism called the Satake isomorphism, which is in its own right a non-Archimedean generalization of this thing Harishchandra. So we've gotten close to computing Harishchandra, and then we're only two isomorphisms away from having this kind of computational introduction to how we built up these L functions. So and hopefully once you do one, it becomes increasingly easy to do the other. So anyway, that's a little motivation. Harishchandra, an Indian, somewhat underrated, probably drastically underrated mathematician who's kind of provides a lot of the kind of Lie theoretical underpinnings to Langland. Yeah. Well, is that it? Maybe so. But next week I think we'll be heavier on the L, and on the L. Yeah.
I don't know if isomorphism between some polynomial algebras are really that interesting. Like, to show like they're not gonna produce the picture that you have in the background, right?
Well, we already have those, so that's not that exciting. Yeah, well, we'll personally be excited, and hopefully our enthusiasm will carry the presentation. Okay, well, Cola, Carlos.
Oh, I can show some, I don't know, some work I've been doing on the trying to rework how hypergraph rules work in a way, how the patterns are created from the rules themselves, and the work in progress, because it's kind of design problem, I think, mostly. So here, so just typical example, you have a hypergraph as a target hypergraph and a rule that you're trying to apply a rule to the hypergraph, right? And the problem is that usually when you have this hypergraph, when we turn it into a pattern like this, right? So we have two edges, a binary edge, another edge. If you turn this couple of edges into patterns, you kind of have this typical pattern symbols in the language, and they usually, if you try to pattern match with them, they can bind to anything, right? So there's no condition that they should be distinct. But if you actually treat some hypergraph structure, if you actually like just look at it, those vertices are kind of look distinct. So maybe it makes sense to always have this condition. Okay, they can't bind to the same thing. So and now we're kind of experimenting. Okay, we should put this condition always as our condition when we do this kind of pattern matching. When we turn this left-hand side of the rule to pattern, in addition to making those pattern variables, we also add some condition they should be distinct. Okay.
Yeah, and
also,
just to add on that point for everyone's clarification, one of the reasons why we are trying to enforce this at this level, and I hope Nick would agree from our last conversation on this topic, is that we're eventually going to add labels to the vertices, so you can have the situation where you have like repeated patterns that match, right?
I was going to explain labels.
Okay, perfect. Yeah, sorry. Go ahead. Yeah, I didn't know where you were going.
So as you can see, it's also hypergraphs can have labels as usual as for graphs, but now we want to kind of add some semantic meaning to those labels, not just some visual, tooltips on the visualization of the hypergraph itself. But when you have some labels, on the left-hand side, they kind of treat it semantically somehow differently. So, for example, when you do the pattern matching, when you make the hypergraph into a pattern here, also you see that it's like this thing is actually labeled pattern. If in input form, it actually called label, right? In the standard form, it looks like this. It's very weird, right? So,
so that final form it's the labeling below?
So this is just will match everything, right? So basically this is the labeled vertex. We have assigned some pattern symbol to this vertex, and label can be anything, right? But when I specify some explicit label, like I say for this vertex, have label X, right? So this X appears here. So now when I use this hypergraph, for example, on the left-hand side of my rule, and I would try to match it against the hypergraph, it would only match a vertex with this explicit label. It wouldn't match any vertex, like this one, which says that I can match vertex, this x1 gonna bind to this vertex, and I can bind to any label. But this should match only to the vertex with this label, okay? And I basically can use any pattern here. Maybe I have some named labels for my vertices, and now the only allowable vertices to match against would only allow to this form, right? So that's kind of the design at this point. So basically make all the default bindings should be distinct, but when you want to impose some kind of equality, you should do it for labels. In labels, for example, if I want label number, vertex number 1 and number 2 to have the same pattern, I just make it like this, I guess, right? And now they would require to match the same kind of label in a way. But in a way, this constraint should go away, and I'm kind of thinking how to impose it. I guess when the labels are none, I don't know what to do. So I'm thinking how to design it properly. It's like this condition kind of still, in a way, of matching to the same label.
So this is mostly wrestling with the fact that that's how Mathematica does pattern matching, right?
Yeah, I'm just trying to make these two languages coincide itself. I want to rewrite into using hypergraphs, and what would be the corresponding Wolfram language pattern. That would make sense, right?
Yes.
Given like labels and vertices and so on.
Well, looks very good. I'm very glad to see that.
Richard, I saw you. Not to pick on people, even though I do that all the time. I saw you kind of nodding along. I don't know.
No, I just it's related to the conversation that Carlos and I were having on the conditional rewriting stuff because we're essentially just using Mathematica's conditional pattern, the slash semicolon thing to impose arbitrary constraints on the rule. I mean, you could do stuff like, for example, if you had numerical vertex labels, you could say that x1 is less than x. You could put some inequalities or do some. You know what I mean? You could get quite creative with how you describe the rules. I mean, I'm not sure that there's an obvious sort of practical use case for the example I just gave, but you know, if it's experimental computational exploration, then there's always sort of interesting things to explore. And actually, in the field of attributed graph grammars and stuff, there's a lot of stuff there where, you know, you do have values on your vertices and edges, and there's some computations which are happening on those as you do sort of up and down passes through the tree and so forth. And what does that look like? What do attributed hypergraph grammars look like? In fact, I think I did find some examples in the literature. Attributed hypergraph grammar. Attributed context-free hypergraph grammars is the first result I get. And those require these rules with sort of conditions on them. And you can express a lot of things quite powerfully. So let me just try and recall. Where the hell did I see attribute grammars? It was used in some sort of, actually, there was some research group who made this system that came up with some really fast layout engines for so arbitrary user interface stuff. You know, so in your browser, they had to handwrite all these layout things to get CSS to lay out nicely. But these guys made this nice thing where they domain specific language, and then it constructs a attribute grammar, and then eventually they do all sorts of these program synthesis things on it, and they end up with a really fast layout engine automatically, which is guaranteed to work. You know, it's not going to have any bugs because they've formally specified a few things and they've passed stuff off to Z3 and blah blah blah. Anyway, I'm just mentioning this because it was a nice practical application of attribute grammars, and I don't know how much people have played with attributed hypergraph grammars and in a practical setting. So anyway, it's nice to see these conditional hypergraph rules, and it will be fun to play with them.
Well, I was actually thinking of getting rid of those, so it's kind of like I did right now, you know, because
But
potentially because imposing this inequality can be instead performed using labels instead,
Yeah.
right? So like if for example, if I like drop all if my labels are just arbitrary like this, right? This would now allow to bind to the same vertex, right? To this point.
Yeah.
X1 and X2 is allowed to bind, but labels, given label like this, would disallow this immediately.
Mm-hmm.
So it's kind of maybe instead of giving this condition always that all our vertices are only distinct, maybe you should do it other way around. They should kind of be arbitrary, but when you want to impose this, that they can be the same. But I'm not sure. This kind of maybe you should allow both. Some kind of weird option to control.
And then it allows to do crazy things like I mentioned. Like for example, you know, the rewrite rule does some arithmetic on the labels in order to calculate the new labels or something. I don't know, whatever. Someone might come up with a need for that, or maybe they're not integers. Maybe you've got some real numbers and you're doing some. I don't know. If this rule matches, then the next hyperedge is the cosine of, I don't know. Do you see what I mean? Like, I don't know if I'm communicating it correctly, but it's like if the rewrite rules have some interesting conditions, you know, which can be expressed using Wolfram language, arbitrary expressions, and on the right hand side of the rule, the replacement, you can do arbitrary computations to calculate the actual replacement, then I mean, we were talking about this before the stream, this hypergraphs as first-class citizens. With Carlos, I was discussing the idea of like a hypergraph rewrite-based programming language. And that's maybe how I would see it manifesting. I don't know.
Yeah.
Anyway, sorry if I'm totally off topic.
No, that's
I like.
that's kind of what we're doing, some kind of DSL for hypergraph rewriting. It's gonna be a language within a language.
Yeah. Yeah, that'll be super interesting. I mean, this is exciting to see pan out. Something else you wanted to show, Nick?
No, nothing related to hypergraphs, I guess.
Okay, because I guess briefly, we don't have much time, but quite coincidentally, I'm just going to basically leave it for next week because I had prepared small lecture on going from hypergraphs to diagrams and all the business about labeled hypergraphs. I mean, I'm not even going to connect mine, but you can see I had it ready here in my tablet.
Well, how much time do you have, Carlos? I mean, you're the person who has to go first, so it's up to you, I think.
I mean, I would rather, comment briefly on what's going on, and because I prefer to have plenty of time to just explain, and because I have to draw by hand, and I don't have everything drawn. I like to go slowly with diagrams and so on.
Yeah, sure.
So I'll do this.
And now you're in Richard's position, and so now next week.
But because I want to also use this space with the viewers that we have and the people who might watch this later on also, because Memes of Distraction said, "Is Carlos Morpheus?" in the chat because of the Matrix references. I'm going to take the opportunity and make the official announcement of the upcoming event.
He's functorious.
So, oops, where's this? So, yeah, here we go. So I am indeed Morpheus, and I am indeed offering you 2 pills. So yeah, I'm happy to be able to finally announce that the Hypermatrix workshop is happening. We have critical mass of confirmations and time availability and everything. So yeah, Hypermatrix workshop is happening. The offer, I mean, some people actually asked what is being offered, red versus blue. So in case it's not clear, it's higher order structures versus binary lower order structures. That's sort of the dichotomy here. So we have confirmed. I wanted to show the website. This is available, by the way. I'm going to post it publicly. I made it public recently, so we'll post it here. I will post it on Twitch, and I will post it on the Discord as well. So we have these confirmed speakers. I mean, we have 5 confirmed. There should be 2 more that send me their abstracts and talks, but for now we have these 5 for sure. So Tali Bainan, someone who is in the Wolfram sphere, a lot of people will know about him. He's going to talk about rainbow arrays. And by the way, all the information about the talks is down here, so you can actually go to the website and get all the information. Then Eddie Nagan is going to talk about complexity of hypermatrix equivalence. So it's going to be exciting to mostly, I mean, I'm more excited about the concept of hypermatrix equivalence that he puts forward. I wonder if, I imagine he's going to be, because I don't think the abstract gives away, let me see, equivalence of matrices defined relative matrix group actions are crucial. In this talk we'll discuss how equivalence class of hypermatrix define relative hypermatrix actions on the basis of hypermatrix algorithms. Yeah, so he doesn't really specify, but I imagine that he's going to use the hypermatrix group action that was in that notes of the Mathematical Society, that you effectively, so it's effectively using what I call the cone product, which is the Bhattacharya-Messner product, which is, it has this 3-way contraction of an index shared by three matrices, and with that, you can use this concept of two matrices give a a single action. You can just, I mean, you can view that as a single operator, and that defines an action of pairs of three matrices on three matrices, and you can start to use more standard notions of equivalence there. So imagine that that's going to be his starting point, and then he's gonna comment on the complexity, and complexity here refers to computational complexity. He's concerned with computational times and computing efficiency of algorithms and things like that for hypermatrices. And in Edina's words, he views complexity as one of the main possible avenues for higher order structures to be solved in some sense. He thinks that it might be possible that these higher order structures make some processes much more efficient, and it's somewhat intuitive with some of the conversations that we've been having, that it might be possible to formally express these higher order operations in terms of pairwise or binary computations, but it might be that the higher order versions are much more efficient when implemented fully. So that would be an interesting talk to listen to. I've never been in a seminar by him, but I've heard a couple of his talks online, and yeah, this research I think is one of the very promising sort of banners of hypermatrices. And then Joshua Groucho is gonna probably present a pretty nice overall picture of hypermatrices and using them in different contexts. Rausch, I think, Michel Rausch, I think, is gonna talk about higher order algebra in the more conventional higher arity sense, although in the context more of the mathematical physics, this one, more in the context of theoretical physics. I mean, these are F-Lie algebras, so yeah, they have some component of more conventional F-ness, which is as far as I understand, just going for high arity, the algebras, and the more conventional structure there. And then finally, for what is confirmed, we have Harm Dirksen that is going to talk about wheeled props. So props are, as you can see from the title here, are product and permutation categories. So these are fairly general systems of basically what people call pasting. What's it? Pasting. Where's the word? I'm missing the word. Pasting formalism. Pasting. I forget about the technical term they use. But basically, you have some notion of pasting diagrams and composing them in this way. So operads are an example of a product and permutation category, and so props are some kind of generalization of operads, and wheeled props have some particular properties that might be interesting. So this is going to be more the categorical approach to many of these structures. So anyway, I wanted to take the time to just advertise this and sort of comment that the lineup is really quite interesting. I think it's very balanced. We have quite a nice spread of topics. It's not like we have 3 category theorists and 1 odd physicist. It's really quite, the different flavors of higher order structures and hypermatrices I think are very well represented. I'm very, very happy with, even if the speakers that haven't replied to me happen to not be available because they have been silent for a few days, and I get the sense that maybe some of them won't be able to make it. But even with the speakers that are confirmed, I think this is a very, very good lineup. I think it's, in fact, I think both Michel and Harm, I think. So 2 of the speakers I didn't know personally replied to me when I sent out the email and the website to say, can you check your information? Is everything looking okay? And so they had the chance to read each other's abstracts. These two people replied to me saying, "Oh, the lineup looks super exciting. I'm looking forward to meeting you during the week." So just to explain, I mean, it's on the website. You can read it here. It's quite summarized at this point, not many details, but you can read that we say this event will take place online and will be comprised of 2 days of talks, the Monday and the Friday. So this is kind of the bookends of the event, and then there will be 3 days that we hope harbor some free-form interaction over Discord and informal Zoom meetings. So this will be articulated on the Wolfram Institute Discord. So we'll have time to basically interact, to ask questions, and we'll have the Institute meeting room available, and people, we'll be able to share that link with people that want to hop on and have a chat. So my idea is that we get some people from the speakers and the audience and the Wolfram Institute community sort of interacting, discussing, throwing ideas around. Because one of the things that I regret when I go to seminars, especially online seminars, but also seminars in person, because they are effectively the same. I mean, it's kind of fascinating how after COVID we've sort of reshuffled in terms of where we are physically, but the seminar structure hasn't changed at all, right? And you get this person, someone introduces them, and then the person spits out all the information, and then there's some couple of very interesting questions, and they're like, all right, and then you never see them again. You never interact really. Maybe you have coffee and that's it, right? And I regret this because when you're minding your business and there's a large department that you're part of, or a large institute that you're part of, and then people come and go. I mean, sure, you sit down, have coffee, have lunch, or whatever, pass the time, and it's a good TV program to watch while you eat. In some sense, it's like sit there, you get some ideas, and it's fine. But I feel like if you want to actually interact and spread the ideas, and especially in this topic that is quite disjointed, and it's these pockets of people around the world working on this topic that is not very connected, I feel like having this week in between to have the time, even to email people and say, will you have a time for like a Zoom chat, and just privately, just having the pretext that this week is kind of it's hypermatrix week, so you're somehow interacting on the basis of that, and you're all exchanging information on the basis of that. I think that this has been quite a successful event. It hasn't happened yet, so I mean I will say that at the end, but I feel like by the looks of it, it's looking as good as it could, I think, at this point. So very happy, and inviting everyone to share it, to spread it if you find it interesting, and yes, we will do our part in the coming weeks until the end of April.
Can I come?
Of course,
cool.
You're invited.
Okay. Okay, great. Well, thanks, Carlos, for suggesting and organizing and pitching it. It was quite a good description. Yes, we have red pills with many flavors, category flavor, physics, cherry, raspberry. So yeah, this is going to be fun, and I agree that having some time in between the talks for people to get together and have follow-up conversations is a very good idea.
Yep.
Well, Carlos, do you want to say anything about your actual research, or do you want to just wait until next week?
I think I will just wait, because I mean, instead of saying, I mean, I've been working with Nick on the functions. We've been making some progress there, and I've been theoretically thinking about exactly. I mean, it was very nice what Nick presented, because that's exactly what I had prepared to give the explanation on, which is mostly on how to do the hypergraph rewrite with labels. And so yes, we should whenever, Nick, you feel like you're comfortable with some solution, just let me know, and we can discuss it. But yeah, other than that, on the research itself, just making steady progress. And I did mention it yesterday that it will be part of today, so that's also why I'm not mentioning all this conversation on computer algebra systems, and it has been mentioned already before in today's session. Nothing much else to add. Simply sort of throw my enthusiasm on top of what has been said already. I mean, we are clearly living in a time where the computational systems that we are using and the computer algebra systems that we are using are becoming prominently limiting or prominently enabling in certain ways or limiting in other ways, and I think it's kind of prime time to go after the computer algebra systems of the future. And I think we have good primers here. We have good, problems, open mathematical problems. We have computational systems that are very powerfully describing some phenomena. I mean, I look anywhere from the generative models of the Wolfram Physics Project to sort of complex system simulations and dynamical system simulations and all these kinds of things. And yeah, I feel like this is the sort of the breathing field of a live science. I mean, this is very much going on, right? So yeah, I'm just excited and happy to be on this wave.
Well, we're glad to have you, Carlos. Well, I guess we've already gone. Yeah, I guess that was an hour. Richard did put something in the Zoom chat. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. Carlos, if anyone declines your invitation, you can just send them. You can just send them back below. Well, okay, good. Yeah, this has been fun. We've offered some teaser of things to come next week. A prepared presentation from Carlos, but they're always quite good. And you can, if you want to, you can learn about the somewhat underrated world of Harishchandra, amongst other things, and also this question of a space of Fractran programs as well.
Yeah, that was very cool, actually. I liked it.
Yeah, and other surprises. Well, okay. Well, for the viewers, thank you as always, and we will be happy to chat with you on Discord. You know what? I've been saying this for a little while. I'll put something in Discord this evening, kind of a review of what we discussed during this time, so that someone can ask some question maybe for next time, like who is Harishchandra, or where, can you explain more about Fractran? I don't quite understand. I know Fortran, and I know about fracking. Are those prerequisites okay? And et cetera, et cetera. So I'll put some things in Discord, and then we can go from there.
Sure.
All right, everyone. All right. Well,
Right,
thank
guys.
you all, and yeah, we'll see you next week.
See you next week.
See you later.
Good to see you,
Cheerio.
everyone.